Welcome folks to this tutorial on how to use two important laboratory instruments, which are the function generator and the oscilloscope, which is this instrument over here. So this is the oscilloscope that we're going to learn, and this here is the function generator that we can also learn on how to use in this tutorial. So this is the function generator that we will use in our laboratories. And as introductory to those instruments, what we are interested in is we are interested in generating three signals. The first one will be the sine wave. So if you click here, will be a sine wave. It will basically generate a sine wave signal. This one will generate a square wave, and this one will generate a ramp signal, which is basically a triangular pulse. So if you see here, this basically will be the triangular pulse. So when we use this function generator, we can basically use any of those three signals. So if I'm going to use, for example, the sine wave, here is my sine wave. I can choose it, and then over here I can select what's the frequency or the time period for the sine wave, and I can adjust that. Or I can basically select the amplitude, so I'll tell you what's the peak value or the peak to peak value for it. I can add DC offset to it. I can basically have some phase shift, which is a delay, and I can add more functions to it, but at least at this point that we are interested in changing the frequency, the amplitude, or the DC offset is needed. That's basically where we are interested in. So to adjust the amplitude or the frequency or the DC offset, you can enter the values, the exact values that you wanted to adjust using the keypad over here, or you can use the knob. You can adjust the frequencies using the knob. So if I'm going to select, for example, a sine wave, and I'm going to change the frequencies, I'm going to click on this button. This will change the frequency for us. Right now the frequency is set at 2 kilohertz. So I can adjust it to 1 kilohertz. Basically I will say 1, and then now it will show here 1, and I will choose K, stands for kilo. I can do 1 megahertz, 1 hertz, 1 millihertz, 1 microhertz. So I'll do 1K. That basically will make it 1 kilohertz, basically by entering the exact value. I can say that's going to be 1.25 kilohertz. That will generate a signal will equal to 1.25 kilohertz. I can use the knob to adjust that value. So you can see that the knob, by adjusting the knob here, I'm going to change the value to, for example, it reads now 3.25 kilohertz. And I can move the digit basically by the decimal point, basically the digit, to use the probe by using those keys. So if I move this way, now I can increment the 100th digit. So now it becomes like 3.350 kilohertz. Or I can reduce it so it becomes like 3150 kilohertz. I can move to the next digit, and then I can make that, for example, go to 0, and now this becomes 31 or 3.1 kilohertz or 3100 hertz. So you can adjust basically any of those values, frequency, amplitude, or I can adjust the offset to the DC by clicking into the field, and then I can play with the knob. So if I want to change the amplitude here going to be in peak to peak. It says that peak to peak, the DC offset is 0. So I can adjust the peak to peak value here into 5 volts, 6 volts, 7 volts, 8 volts, 9 volts. I will go to 10, 11, 12 peak to peak. It will go all the way up to 20. And then it will stop. This is the maximum value. So it will go up to 20 volts peak to peak. Okay? And you can do the same thing with the square wave. So if you want to have a square wave, you can adjust the square wave over here. And basically I can adjust the amplitude, right? So here it can be like, for example, 10 volts peak to peak. And then I can also adjust the frequency. I can adjust the DC offset. So I can add values to it or subtract values from it and all that. So those are sine waves, those are time domain signals you can create for testing. Now I'm using the triangular pulse, or what we call the ramp. Right? I can adjust that. And there is other functionalities that we can use that we don't really care about. This for this lab. So we don't care about for this lab, but you can learn it later on when you study advanced, if you want to create advanced signals. What's important here is also we have two channels, which means that we can create two outputs to generate a signal. And in those two outputs over here, we can use channel 1 or channel 2. So if I want to configure the values for channel 1, I click on this button. If I want to move it to channel 2, basically toggles. Now if I click here, it toggles to channel 2. So if I'm going to use channel 2 here and I want to set channel 2, you can see that channel 2 is a sine wave, where channel 1 is actually a triangular pulse. So anything I change now will basically change the channel 2 values. And I'm going to go back to channel 1. So I'm going to basically push on this button and toggle to channel 1. So channel 1 is shown here as a triangular pulse signal. If you wanted to activate channel 1, you push this here. When this is led, that means channel 1 signal will leave from this outlet. This is called a male BNC connector, male BNC connector. So you can send the signal from here into your circuit, for example, or the oscilloscope. If you push on it, that will deactivate it. Channel 2 is the same story. This is the output for channel 2. You can activate it or deactivate it. So usually when we wanted to send the signal, we're going to use something called the splitter, the T-splitter. And the T-splitter is basically a connector that will look like a T. So this is a T-splitter. That is a T-splitter right here. Right? And the T-splitter basically will split this terminal, the output terminal of channel 1, for example, into two signals. The reason we want to do that, if I connect this here, the reason we want to do that is basically now this particular output has been split into two outlets. One outlet can go directly to the scope, and the scope is a device that will be used to measure the signal, and the other output from the splitter can use BNC to alligator clippers, and then that can go directly to your circuit, and then you can test your circuit. So you're going to use one of those outlets to go to the scope to measure the signal, and the other output can go to the circuit. So this becomes the input signal to your circuit. So let me show you how we're going to connect it to the scope, and then let's see how is the scope going to work. So to connect it to the scope, I'm going to use something called BNC to BNC connector. So this is basically a BNC to BNC connector. This becomes a male BNC connector. So I'm going to connect this here, and the other end of the BNC cable will go directly to the scope. And here in the scope I have 4 channels, so I'm using channel 1. We're going to talk about the scope shortly. So the scope, basically, if you look into the scope here, the scope will have 4 channels, and the scope basically is a device that is used to measure the signals. So it's going to measure the signals, and then we'll plot the signals on the screen or the monitor of the oscilloscope. Our scope here has 4 signals: channel 1, channel 2, channel 3, channel 4. The signal of channel 1 going to be yellow, the signal of channel 2 going to be blue, the signal of channel 3 going to be purple, and the signal of channel 4 going to be green color. So those are the colors of the scope that we have, and we're going to use to measure the signals. Now I'm going to enable the output of the ramp signal, and I'm gonna push on the auto set. The auto set basically will read the signal and will decide to make the signal look nice and beautiful like that. The auto set over here will basically give me the dynamic range to show you the best display of the signal that we have. It's auto set. So when we look at the scope will plot the signal as a function of time. So the horizontal axis here gonna be time, and the vertical axis here gonna be voltage. So the scope will measure the voltage versus time, unless you use special probes that are used to measure current or power. But in our lab, we're gonna use probes, and the probes are basically like what I'm holding in my hand right now. It's a device used to measure, to probe the signals, and this generic probe is used to measure the voltage. So here we have the graph of voltage versus time, and now we need to control this. So a couple of the knobs that we are interested in, the first ones are the knobs over here. This is what we call the horizontal, right? So in the horizontal, the most important knob is this one here. This basically says second per division. That basically says that each major division horizontally, how many seconds is it? How many seconds each division is? So each division here gonna read 50 microseconds. So one complete division from one major dot to one major dot here will read 50 microsecond. I can play with the knob. So now I make it 100 microsecond. So now each division will read 100 microsecond. So when you increase the time per division, you're basically gonna show more information in one division. Then you basically compress the signal. You compress the signal by increasing the time per division. That means there is more information in one division. We are compressing the signal. If you compress it even more like that, you have now more signals shown in the screen. Now we have more signals shown in the screen. And if I release it, if I reduce it, now I can zoom in. Basically, I expand the signal. So I can either expand the signal by making the time per division very small. That basically means I'm zooming in. Or I can basically compress the signal. That means I'm zooming out. And that basically means that I'm having more time per division. So time per division is important because you got to use it sometimes to measure the frequency or the time period of your signal. So the second knob that we are interested in is what we call the position, which is this one. This is the time position under the horizontal axis. So this basically will move the position of your signal. Right? So the position of your signal. And this over here, if you look at the arrow over here on the top, this is the zero reference that we are using. So I can move the zero reference to any position that I want it. And then here, what I have here is basically the vertical axis. Things have to do with the vertical axis. But I'm measuring 4 signals at one time. So each signal will have its own keyboard. So this here will be for channel 1, this here will be for channel 2, this here will be for channel 3, and this here will be for channel 4. The most important thing we're going to look at is this knob. This big knob here is basically what we call voltage per division. So how many volts per major division over here? So right now, the way it is set is when we read channel 1 over here, it says that it's 2 volts. So that means 2 volts per division. So we have 2 volts per division here. I can adjust that basically by using the knob back and forth. So here I can make the knob to be 5 volts per division. Now I can make it 2 volts per division. Now it's 1 volt per division. Now it's 0.5 volts per division. That's 500 millivolt per division. 200 millivolt per division. 100 millivolt per division. it will go all the way down to 2 millivolt per division. So, but you know, when you zoomed in, you lost information, right, about the signal. So that's no good. That's why sometimes if we put the auto set, if we push the auto set button, that basically will go back and reset our signal to the best possible value to zoom in. Then what we are interested in is something we call the menu for channel 1. If I'm going to click on channel 1 here, it will show me the menu of channel 1. So basically here it says that I'm doing AC coupling. AC coupling will factor out the DC offset. There is DC offset that can be canceled out. If you want to measure the DC and the AC values, you push this button again, and that will say DC coupling. DC coupling basically means that you are measuring the DC and the AC offset. AC coupling. And then here, this is the ground. Basically, this is the 0 volt, the reference. So I'm going to have the DC coupling here. Then I'm interested in this one where it says that the 1X probe. Because when we measure the signals, we use a device like the one I'm holding in my hand. This is called the probe. This particular probe is actually X10. So X10 probe basically says that whatever I measure, this probe will divide by 10. Then the scope got to multiply by 10. So if I'm using a probe like this, then I'm going to use the 10 option. So this calls the attenuation here, which is the attenuation of the probe. I'm going to use the 10 option. And now if I'm using the 10 option, you can see that the channel will multiply the reading by a factor of 10, because it says that whatever I'm receiving is actually divided by 10, which is not the case here, because the BNC, this particular connector, is actually 1X. 1X means that it didn't divide, it didn't attenuate. However, if I'm going to use this probe will attenuate by a factor of 10. Now, different probes have different attenuations. You have too many options here. It will go all the way up to 1,000, and then it will come back to 1X. So channel 1 is actually 1X. So if you click on menu, you will be interested in DC coupling or AC coupling, and then you are interested in what's the attenuation of the probe gonna be. Right? So this basically, the signal comes in from the function generator, and we can change this basically to another signal that is called sine wave. I'm gonna set the DC offset to be 0. So I'm setting it 0 volts, right? So now I have 0 volt sine wave. I can zoom in if I want it, right? And this particular arrow here, it shows you that this arrow says that this is the reference or the 0 volts for the sine wave. So what I'm going to do next is I'm going to basically use a BNC to alligator clipper to send the signal to a very simple circuit. So here I'm going to use a BNC to alligator clipper into my function generator. So I'm going to go to my function generator over here, and I'm going to connect the BNC cable into the function generator. So right now those two signals will send a 10 volts peak to peak sine wave, and I can use those into my circuit. The red line gonna be the positive, the black line gonna be the negative, and I have a very simple circuit over here, very simple circuit that I'm using, which is a voltage divider circuit, 2 resistors in series. So I'm going to connect the positive voltage into this input and the negative voltage into this input. So clearly that now I have 2 resistors in series. This is the input signal. This resistor is in series with this resistor, and this is our reference or ground. And now what I'm going to do is I'm going to come to the scope, and I'm going to use a probe. So I'm going to use this probe. Now this probe has the option of making 10x or 1x. It has this knob where I can change it from 10x to 1x. So I'll make sure it's a 1x, and then I will connect that to channel 2. So now this probe is connected to channel 2. Now in this particular BNC connector, it's basically saying that this connector has a positive value and the ground. This BNC connector defines what's the ground for this signal, which is the same as the ground of the function generator. Now all of the grounds become common. So you can see that over here it says that all the grounds gonna be common. So the ground of this probe and this probe and this probe gonna be the same as the ground of this probe. Once you define the ground for one channel, it's going to be the same ground for all channels. Then when we use the probes and the scope to measure signals in a circuit, we're going to be interested in the nodal voltages. Now I'm going to click on the menu for button 2. Now I start to see the button 2. You can see the line is thick. Basically it's measuring some noise, and it is X1 probe. So I'm going to use X1 here. And I'm going to do DC coupling. So I'm going to measure DC coupling. I'm going to come to my circuit over here, and then I'm going to measure the voltage in the intermediate node. So you can see that the signal is too big. And the reason the signal is too big, because the volts per division here is 50 millivolt. So I need to increase the volt per division. So I'm going to keep increasing it. And now I have about 500 millivolt per division. So you can see that the voltage at this particular node going to be less than the voltage of the input signal, because we have some voltage divider circuit. And basically that's what we have here is the plot of V out versus the plot of VI. Because this circuit is a pure resistive, if the input signal is a sine wave, the output signal is going to be the same sine wave. The same shape of sine wave at the same frequency. The only thing going to change is basically the amplitude proportional to KVL, KCL, and Ohm's law. We can change the signal now to a square wave. You can see it's almost the same thing, right? So you can see that the yellow line is the input signal with a voltage per division is 2 volts, and the output line is basically the blue signal with a voltage per division of 500 millivolt, which is much less than the input signal. Clearly there is a relationship of roughly 1 to 4 or 1 to 3 between those two resistors as we speak. You can change it to a ramp voltage. You will also experience the same thing, right? So you're going to have both signals, the input and the output signals, going to be basically a triangular pulse. And what is important here is what we call the peak-to-peak value, and that will basically tell you what's the measurements are. So to measure the values, you need to calculate the number of divisions times the division per volts, and to measure the frequency, you need to basically calculate the number of divisions times the seconds per division. So, and that basically will tell you what's the time period is, and from there you can calculate the frequency. I hope this tutorial helped you in how to navigate the two instruments that we're going to use in our lab in this Introduction to Circuit Laboratory here at Washington State University. And thank you so much for watching this video.